Hello, and welcome to this video, which will be the first in an extensive series explaining various different things in C++. The goal for this first lesson is to ease into things with a simple example. The lessons will grow in complexity as time passes. All of the examples are based off of the books that I have read, and the title represents the book the example was taken from, such that anyone who wants to understand what they are reading a little bit better and decides to research YouTube for helpful videos finds these videos. So the first thing I would like to articulate in this particular lesson is two primary points of concern. So there are two primary points to understand before you begin this series. And the first point is this. As I wish to challenge myself for various different reasons, I will be talking off the cuff and only guided by a document that dictates the general structure of the lesson. A consequence of this is that I may forget to articulate an important concept or say or write something that is inaccurate. However, the overall concepts concerned should be accurate. And the second point is this. The lessons will be verbose and employ heavy use of repetition to aid learning, and for those who want to understand some of the more complex examples a little better. If you are not a fan of this approach, then this series may not be for you. If you are, however, then this series will cater to you. However, with respect to the first point, the first lesson will be an exception. I will make use of a script in a few places, including the introduction and when we discuss something called the move constructor. With respect to the video schedule, it will be every weekend. In terms of the knowledge requirements for this series, an understanding of the basics of C++ will be helpful, but I will try to explain most things that we encounter. Also note that the lessons will be done by writing in Paint, as I prefer to do these kinds of things that way. Okay. Now, let us outline the topics that will be covered over the next several weeks. So the first, there are several different. I suppose I'm thinking of calling the series C++ by example, because it's not teaching you C++ in the sense that it teaches you the basic facilities and then builds upon that by introducing more complicated features. It basically just, the series is aimed towards taking different code fragments that solve different problems in terms of whether it may be, for instance, a text query program, or whether it may be writing a matrix class that can perform different mathematical operations that mathematicians expect of a matrix and so on. The point is this. We'll go over several different examples. It's all about just taking examples that solve some specified problem and explaining them in a way that's relatively simplified. And of course, I did mention previously that an understanding of the basic foundations of the C++ language will be helpful, but it's not critical because I will try to explain most things as we go along. Although it's difficult because I could explain absolutely every facility used in the sense that I would explain every little nuance that can arise given its employment, but that would be too time consuming, so only the general concepts will be articulated. For instance, when you talk about classes, there's a great deal of complexity with respect to classes, but I suppose, and I will get on to discuss this at some point in this lesson, I suppose the most important thing to understand about the class mechanism is that it is C++'s main support for the creation of abstractions. And in principle, it groups together two different kinds of entities, member functions and data members. But so here's the general idea. So we're going to go through different books. The different books have different examples in them, and I would like to cover them. And so what I would say is this: we have C++. I read a book called C++ Primer 5th Edition, and there are 4 examples in that book that I identified as being candidates for lessons, and so consequently that will probably turn out to be the case. Uh, I had mentioned previously the notion of a text query program. That is one of the examples that will be covered, and so on. Now, after we do C++ Primer 5th Edition, I will do an overview of the C++ programming language, and that will probably take a few weeks. And now I'm gonna speed run through all the different other examples that I'm going to discuss. Excuse me, that's actually incorrect. Before I cover the entire I'm not going to cover the entire C++ language in the sense I'll write a paper that's 1,000 pages long and it will cover every single detail of the language. It will be a general overview of its most important components. But before we do that, I will actually do I will teach a vector implementation as outlined in C++ Primer 5th Edition. So that's the first point. After we do that, we will do an overview of the C++ programming language, and then we'll go to the C++ programming language book by Bjorn Struisrup, and for the sake of simplicity, the next couple of examples, unless otherwise specified, pertain to the C++ programming language by Bjorn Struisrup. I will do a vector implementation, a string implementation, and a matrix implementation. The matrix implementation is probably, out of those 3 particular options, the most complex, that will require the most time to articulate. Now once we do that, we're going to move on to cover something called SFI-NAE, and in particular SFI-NAE based traits. We're then going to talk about using generic lambdas for SFI-NAE. We're going to talk about detecting members. In other words, it is possible to employ, or it is possible to abuse the SFI-NAE. Well, I suppose it's not an abuse, because in modern C++, it's actually a principle that has been expanded with the sole purpose of enabling these kinds of techniques. But the general idea is that we can use the SFI-NAE principle, which is a general principle that applies in various different contexts, in order to check if a particular, for instance, data member with a particular name exists within a particular class specification. And so consequently we will cover that. We'll then cover type lists, tuples, and we'll cover discriminated unions, a variant implementation. That will be a relatively complex example as well, and then we'll cover something called expression templates. So as you can see, we're not quite done yet. There will also be engineering problems such as terrain navigation for something like the Mars rover, and artificial intelligence, and others. So as you can see, there are various different things that I've spoken about in terms of what's going to be covered. It's just a matter of time before we get to each particular lesson. Okay. So here's what I would like to discuss. Before we actually get into the example of today's lesson, here's something I would like to discuss because it is of great importance. Now, as this is the first lesson, I would like to emphasize the following 3 points. The first point is this: once you learn the basics of a programming language, the difficulty does not arise in literally interpreting code fragments, but rather in understanding their logical foundations. Point number 2. If you're having difficulty understanding these logical foundations, one must proceed to talk through the code fragment in a way that reflects directly the facilities and features used. In other words, literally interpret it. For example, and we're going to write something down now. We're going to write some, and again, I'm doing this in Paint because I prefer to do it this way in with these kind of things. So, for example, for the following code fragment, we may proceed to analyze it as follows. So let's write out some code, some C++ code, and we'll explain it momentarily. We're almost finished. It's gone very. It's not a very nice. It's not very nicely laid out, but it is. We can deal with it. We can deal with it. So, just to reiterate, what we're trying to strive towards here is we're trying to get to a point whereby we can understand the logical foundations of a particular program. In other words, we want to understand the service every statement provides in the overall solution of the problem that we're trying to address. Whatever that problem may be, we're trying to understand what does the expression, what is a particular expression, what does a particular function call represent in terms of semantics, in terms of achieving some specified logical objective. So, first, taking into consideration the code beginning at point V, and I have not, that's point V. We have the declaration of a function template. How do we know it's the declaration of a function template? And again, I must add this. What is a template? The template is a mechanism that enables you to... There's two things here that I would like to discuss. The first point is not one of concern at this present time, and that is that the template mechanism is a mechanism that can be employed in order to aid in the computation of certain things at compile time. But I suppose the simplest aspect to templates is the one that you probably first learn about whenever you read a book on C++, which is that templates are C++'s primary mechanism for defining general abstractions, in the sense that we can define a general solution that can apply to a wide variety of different types. In other words, if we have for instance, an example of this is in the standard library, there are different functions. Now, of course, you have to understand that with respect to templates, and again, I've been reading a book recently, and we can employ all sorts of different techniques. Let's make this simple. So, The first point I would like to note is that the template is an ability, is a mechanism for providing a general solution to a particular problem that can apply to a wide variety of different types. And with respect to for instance, a function template, the implementation of a function template implicitly constrains the types that it can be instantiated with, because, for instance, if we instantiate a function template with a type whereby that particular type is used in the declaration of a variable that goes on to use a particular operation, for instance, the dereference operator, that type with which it was instantiated does not support, then that's going to lead to an error. And so consequently, you have to understand that the template implementation itself actually imposes a certain level of constraint on the types that can be applied to it. Now, in terms of actually being able to verify that a particular set of template arguments satisfy the requirements of the implementation of the template, there are various different ways to do that. For instance, SFI, NAE techniques. But I was reading a book relatively recently, this C++ templates, and it talks about the next C++ standard potentially bringing in support for something called concepts, which is essentially a mechanism for specifying all the different constraints that an implementation imposes on the types with which it is instantiated, and it prohibits instantiation of the particular function template if it is instantiated with a type or there is an attempt to instantiate it with a type that does not meet the requirements of the template implementation. So, let's begin again. Starting from the beginning, at point V, we have the declaration of a function template whereby so how do we know it's a function template? Because it uses this notation here. I'll outline this in purple. So we're using the notation template, and then we supply angle brackets, and then for the moment being, we need not concern ourselves with this. We just know that we're declaring a template, and in this case, it is a function template. As we can tell, we'll get onto that in a second. So, it's a declaration of a function template whereby the first template parameter is a template type parameter. So the first parameter is a template type parameter, which is this. And a template type parameter in the declaration of a template is preceded by the keyword type name, and it can be equivalently replaced with the keyword class. There is no difference, technically speaking, and what this represents is a parameter that is supposed to be synonymous with a particular type with which it is instantiated. So that's fine. And the second is a template parameter that uses the variadic template mechanism to enable transmission of an arbitrary amount of values of differing types. And that is, one second, this particular parameter here. And as you can see, these dots weren't just put there for no reason. This is a notation that basically specifies that it is an entity that is able to capture an arbitrary amount of objects of different types. In other words, we could, typically speaking, with respect to a function, suppose we have a function with a single argument. That function therefore expects a function with a single parameter, I should say. In order to use that function, we must specify the value for that parameter by means of the supply of an argument for it. But what we can do, and again, before I proceed to discuss this, I haven't really read about this at all, about templates being discussed in this way at all. But this is the way I like to think about it. I like to think about this as the interface of the template. In other words, it represents the means by which you interact with its implementation. And that's important. And now, I'm not quite sure what I was saying. Uh, so I think I was discussing this type name here. Basically, to make it be succinct, we will continue on that. So the second parameter, the second template parameter is a template parameter that uses the variadic template mechanism to enable transmission of an arbitrary amount of values of differing types. The function is specified to return void, and the interface is defined to accept an object whose type can be deduced if we do not explicitly specify it, and the second is defined to be a function parameter pack that is capable of capturing the types and values of an arbitrary amount of objects. Once again, template argument deduction can implicitly determine the template parameters for a call of the form, and this is a call of the following form. Suppose we said print A, B, C. In this particular case, A, B, and C are objects of type int, double, and char respectively. Thus, the type of the first actual parameter is determined to int, and the parameter pack captures the types double and char in that order. To fully generalize, and again, keep in mind where this all began, we are trying to literally interpret this particular code fragment here. We're not trying to understand its logical foundations in terms of what logical service it provides in the solution to the problem that we're trying to address. We are just trying to take the first step in obtaining that knowledge by means of actually understanding the literal interpretation of a particular code fragment. So that's important to understand. And so we will proceed as follows. To fully generalize, the first statement within the implementation, and when we refer to the implementation, we refer to in this particular case, these statements here. These statements are executed in this particular case in a sequential fashion whenever we invoke the function print. And I suppose the notion of what a function represents is actually a relatively simple one, and there are numerous analogies that one could invent to explain it to a novice programmer. And the first analogy is this. Suppose you want to make a sandwich. What do you do when you make a sandwich? You get pieces of bread, you get butter, you put in the chicken, you put in whatever you need to do, and then you package it up or whatever. It's analogous to a function in the sense that a function is a unit of computation that can be invoked, and when we invoke it, it executes the statements contained within its implementation, in other words, its body, in a sequential fashion in the absence of multi-threading techniques. How is that analogous to making a sandwich? For two reasons. Number one, we can specify that the procedure for making a sandwich be initiated by telling someone, make me a sandwich. You don't have to tell them, can you please get bread and butter it and get chicken, get red sauce, whatever it may be. You can before anything, sometime previous, perhaps the previous day, you can say, okay, every time I say make a sandwich, these are the steps that you do. And consequently, the next day you say make a sandwich, they know what to do. They execute those statements in a sequential fashion in order to achieve some specified, some desirable result. Now, I suppose there's a subtlety in this, and you perhaps already noticed it. And the subtlety is this. The function notation leads to less code bloat, as it's referred to in various different books I read. In other words, suppose you have a function that, just talk for instance about computing the magnitude of a vector in three-dimensional space. In order to do that, we have to apply Pythagoras' theorem twice in succession in three-dimensional space in order to obtain the magnitude. And suppose we're running a three-dimensional application that needs to do this kind of computation multiple times throughout the source code in order to do something useful. We could, in theory, just repeatedly specify the different instructions in the different places that we need them. Or we could be more efficient than that. We could alternatively specify those instructions in a particular function, and then call that function whenever we need to throughout the source code. So that's one of the benefits. So let's continue where we left off. This will invoke the appropriate implementation or unit of computation. In this case, it is a function built into the language. We'll get on to discuss that in a moment. Now, we note that the sub-expression we just observed okay, I skipped ahead a bit, so let's go back to the beginning. Just everything I said over the past 20 seconds, just don't forget I said that, and I will repeat myself. Okay, so let's go back to where we left off. To fully generalize, the first statement within the implementation employs the use of the bitwise left shift operator, whereby the operands are an object of type cout, which is this object here, and the type of the first parameter. In other words, whatever type this particular variable resolves itself to be. This will invoke the appropriate implementation or unit of computation. In this case, it is a function built into the language. Now, we note that the sub-expression we just observed is just that, and so we must reason about the statement in its entirety. We know that the employment of the operator will return some value, and that forms the left-hand operand of the second operator. In this case, the implementation returns the left-hand operand, thus enabling us to chain a series of calls to the output operators for the different objects of differing types in a single statement. We can view as a consequence of the employment of the single operator concerned, and thus the invariant associativity and precedence levels across the statement, the evaluation of the expression in the following way. In other words, taking a look at this particular expression here, where we say, whenever you first learn C++, whenever you learn C++, you don't have as much of a sophisticated understanding of what's going on in these kinds of statements. It tends to be described in a way that's inaccurate in order to, and that's not a bad thing, by the way. You know, it's okay to provide helpful techniques in order to better understand how code will behave, but ultimately, when you read more about these things, you begin to learn how they actually function. But I suppose what I'm saying is that whenever you initially learn C++, we just the books tend to refer to this as the output operator, and they conceptualize about it in the following way. They say that we take F and we put it out to cout. Now, of course, in reality, notationally speaking, that may be the intention of the designers of this particular implementation, but technically speaking, what's actually happening here is a function is being invoked, and that function does some kind of work, whatever it may be, and it returns some value if it does it all, if it's specified to do so, and so on. But anyways, pay close attention to this particular expression here. What happens is, let's get a different color for this. That's not going to do. Cout, we'll call it output operator for the sake of argument, F. That executes. And that invokes some unit of computation that does some kind of work. In this case, it's going to, if we assume that F is a built-in type, then in this particular case, it's going to print that the value of that built-in type to the console window, and then it will return a result. Now, and the result that it returns is this left-hand operand. What's this left-hand operand? It's this object here, cout. And so consequently, this entire statement resolves itself to cout. And it consequently forms the left-hand operand of this particular operator here. And so consequently, we end up with that. And of course, that prints a space, and then we have a terminating token. This is quite messy, I do understand that. So, the literal interpretation of the final expression is very simply that of a function call that uses and again we're discussing this the call to print, which is here. The literal interpretation of the final expression is very simply that of a function call that uses the pack expansion mechanism to split the parameter pack into its constituent parts and invoke the function concerned. This is a recursive call, the meaning of which we will explain in the next section. One moment. Okay. So, I suppose what we'll do is we'll just go down a little bit here. And the following remarks are going to reference this particular function. Okay. The code that you're looking at now is the specification of a function that returns no value as indicated by the keyword void, with no parameters and no statements to execute. Note, this is not a template, but is considered in the case whereby the arguments matches interface suitably. Now, the next thing I would like to discuss is bridging the gap. There is perhaps a single step between literal interpretation and true understanding of the logical service each statement provides in order to provide program behavior that solves some specified problem. That is understanding what should be referred to as pure logic. In other words, to be concrete, we conclude the following from the code fragment. Let's go back up to the code fragment. With respect to the recursive function invocation, the syntax employs pack expansion, which means that the first... One second. With respect to the recursive function invocation, the syntax employs pack expansion, which means that the first object is passed to the first function parameter of print, which perfectly captures the type and state, and the remaining elements are passed to the variadic mechanism to form the parameter pack for the next function on the call stack, and so on. In other words, what we're discussing here is that suppose we are within the context of the implementation of the template version of the print function, and we're calling it as follows, as we did previously. X is a parameter pack and it expands. Let's suppose for the sake of argument that it contained the values int, double, the types int, double, and char. What would happen in this particular case? Well, the pack expansion would dictate that we should expand the parameter pack into its constituent elements, and that means that the call expands to the following. Now, this is clearly not the function taking no arguments, the function with no parameters, is clearly not a candidate for this particular invocation because there is a mismatch between the amount of arguments and the amount of parameters. However, the template version is a candidate, and as we can observe from the specification of the template interface, what's going to happen is int is going to be passed to the first parameter, which is simply a type parameter. We'll just say type param. And these two particular elements here are passed to the parameter pack, and that forms the parameter pack for the next call on the function stack. And so consequently, when we recurse and call print again, let me undo that. When we recurse and call print again, there's a pack expansion. What does the pack consist of? Double and char. We expand that, and we get double, char, and double is then passed to the interface of print, and its type is captured perfectly, and char is what makes up the parameter pack of the template. Okay, and so on. The next thing I would like to discuss is understanding the logical foundations. Understanding the logical foundations of a particular code fragment, which may include the analyzation of the wider context. Okay, here's a particularly important example that we're going to discuss now. Consider some, so here's my proposition. Consider some arbitrary mathematical expressions such as the following: x plus y multiplied by k. It is a trivial task to literally interpret this expression. To generalize, we multiply the value of k with y and add the result to x. Simple enough. This relates to our first step. However, we are more interested in what service this expression provides in the solution of the wider problem. Something like the expression relates to the obtainment of an index into an array representation, which is one-dimensional in nature and allocates its elements contiguously in memory, but must provide the semantics of, for instance, a matrix. And so we can say that k is a constant that relates to the amount of elements per matrix row. We dynamically assign y to obtain the ith row, and the x variable represents the selection of a particular element from that row. Thus we have associated an important meaning to this mathematical expression that enables us to understand its logical role in the program. Now, relating to our example, we can summarize thus. So in other words, we're going back up to our example, and it's quite messy now. Perhaps I will write it out again. So we have type name. No, not type name. Template. Type name. X. Type name. What did I call this? T. Oh, that's wrong. And of course it returns no value, as previously discussed. X. Okay. Let me specify the implementation, which does the following. We'll just be very brief here. We'll not even care about spaces. That's too many dots. Okay. So let us discuss the logical foundations of this particular code fragment. It also takes into consideration the non-template version. The function pair is designed to print to the console window the values of an arbitrary amount of objects. This is achieved by recursive instantiation, and the terminating case for when the inevitability of an empty parameter pack arises is invoked to end the recursion. We then unwind the function call stack, which has no immediate or obvious consequences for our implementation, and proceed to the next instruction. Thus, the following principle is a very important one. The most difficult yet important part of understanding a program is not in understanding its literal content, nor its pure logic, but in understanding its logical foundations. All three steps are very helpful in achieving this ideal, but we will consider pure logic next in our third and final point. Okay, point number 3. And again, remember where we started here. We were discussing a few important points that I would like to discuss before we get into the complexities of the different examples. The example today is a very trivial example. It's not too complicated at all, but that's just to ease into things and so on. Also, just to teach the kind of style that I like to employ and so on. So, point number 3. If you still have difficulty in deriving the logical foundations of a program, attempt to understand its pure logic and the picture should emerge. This is most effective when reasoning about a particular code fragment in isolation, hypothesizing about its inputs, and computing the consequences of that input by carefully considering, for instance, the conditions under which a particular code fragment is executed and in what logical circumstance. Consider careful tracing of a for loop. So we're going to write some information here. I have a note with respect to this particular statement. Put an arrow beside it. Note, the auto-type deduction mechanism is implemented in terms of template argument deduction, where we effectively replace a specifier with an invented template type parameter and proceed with deduction. Once template deduction logic is implemented, it is easy to implement this facility in terms of it and delegate the complex work of actually determining what the type should be to another system. Note this incurs no runtime cost, as template argument deduction takes place at compile time. Thus, this is not obviously a problem in the domain of runtime efficiency considerations. So let us move on to discuss a relatively simple for loop as follows. So really what we're trying to discuss here is pure logic. That's what we're trying to discuss. To understand the pure logic of this code, it is necessary to be able to literally interpret it first. Once we can do that, we can come to the following conclusion. The logic is as follows. K begins at 0. So these are different steps. In fact, we'll write these out. Point number 1. Again, it's about analyzing the pure logic. So in this particular case, K begins at 1. That's the first point. The next point, we check, and again, if you don't understand how for loops are implemented, for loops are one of the mechanisms in the C++ language that enable repeated execution of a particular body of statements, so long as some target expression is satisfied in terms of its Boolean validity. And what that means is that in this particular case, this expression yields true. Now, there are different parts to a for statement. You know, it's interestingly enough, once you implement a facility like while, the while loop, there is no immediate logical reasoning. I suppose I should say there's no technical reason why one should have to implement the for loop, because you can implement any logic of a for and you can implement any logic implemented in terms of a for loop and a while loop. And so one could justifiably ask, what's the point of a for loop? And in my opinion, the for loop is actually quite a good mechanism because it groups different entities together into the same construct and makes clear their relationship. And so, for instance, if we just employ the use of a while loop and then externally, before that while loop was encountered, declared some variable, it would not be immediately obvious that that variable had an intricate connection with respect to the while loop. And so consequently, the for loop is useful because it groups together all these different pieces of information such that we can reason about it a little bit better. In other words, it groups things that should logically be together. But the different parts of the for loop, I suppose I'll just go through quickly. This is called the initialization portion. This is called the test. This is called the statement. And this is called the action. And what we do is we execute the initialization portion. In this case, we're not going to discuss this at length because it's not of concern at this moment in time. We declare an object we declare a variable called k, and we initialize it with a value of 1, the type of which will be deduced. We then check if k is less than 4. If that's the case, in other words, if k is less than 4, which is equivalent to asking upon first iteration, is 1 less than 4, upon asking that question, the result will be true, and so consequently we will execute this particular statement here, and once we do that we increment k. Now here's the interesting thing. We do not go to here. Instead we go here. We only execute the initialization portion once, and then we check this expression again, and if it evaluates to true, we execute the body once more, conduct the action, conduct the check, and so on and so forth. A relatively simple mechanism. But very effective. So, as I was saying, we check the wrong color. We check k against 4. Okay, if the check succeeds, I'll not write this down, but if the check succeeds, we use compound multiplication to increase the value of x, and here's the next step. We increment k and begin at step 2. Note we should also be keeping track of the values of the different variables at the different times. And when we do this, we come to the conclusion that we obtain the value 60 for x. We can then proceed to understand the logical service this code provides. So in terms of things my introduction to this first lesson, those are the general points I would like to get across. Just understanding that the most important thing about understanding any program is understanding its logical foundations. That's extremely important. But anyways, let's get into a concrete example now. So let's actually get some substance into this tutorial or lesson. Tutorial or lesson. Okay. The first point I would like to talk about is copy control and resource management. What copy control pertains to is the specification of what should happen whenever we want to copy an object of some specified type into an object of the same type. And in C++, the main facility for creating user-defined types is the class mechanism. And that class mechanism is a relatively simple one, as we will discover throughout this particular lesson. And in particular, the class itself actually determines what happens in contexts whereby it is copied. And it makes use of different specialized member functions in order to specify what happens in those circumstances, like copy constructors and so on. And so the question now arises, when do we need to, because the point is this, if you do not explicitly specify any constructors, copy constructors, so on, the compiler will automatically synthesize them for you. And so you would say, well, why would I ever specify them if the compiler will take care of it for me, what purpose would that be? And the purpose is this: it all relates to resource management. When you're talking about resource management, in other words, classes that refer to dynamic memory, you have to implement custom constructors, copy constructors, move constructors, copy assignment operators, and so on, in order to achieve results that are in line with what we would logically expect. And so that's the first point. So we discuss what copy control is and why it's needed. And in particular, it is most prevalent in the presence of resource management. In other words, when you're working with memory. The next point I would like to discuss is value-like versus pointer-like. So here's the idea. Suppose we have a class type and we want to specify what it means to copy an object of that type. There are two main approaches that one can come to, or that one can reason about when it comes to, there are two main approaches to choose from when it comes to implementing a solution to the problem. And that is either implementing the copy operation to be value-like or implementing it to be pointer-like. And to be succinct, value-like means that the different objects concerned maintain their absolute independence from one another, but their states are equivalent. And so what that means is that, for instance, two objects that are different instances of the same class type should not be referring to the same location in memory, because that way they are not independent. I suppose they can be practically dependent in the sense that after the copy operation, the representation uh, contains the same values, but the important thing to observe is that any modification of the representation is not going to affect the opposing object. So here, to summarize, value-like means that we have different objects that maintain their absolute independence and bear no relationship to one another. The second approach is pointer-like, and pointer-like is an approach whereby different objects share the same state in terms of their underlying representation. And the most simple example of this is two objects pointing to the same location in dynamic memory, not by mere coincidence, but by design. So, let us discuss how we can provide value-like behavior. To provide value-like behavior, each object has its own copy of the resources concerned. So let's write some code. So let's get into the main example of today's lesson. And again, I will try to discuss as much as I can. I'll discuss that this is where it's helpful to understand the basics of the C++ programming language, but I will get on to discuss what a class is near the end of the lesson. But I will nevertheless touch upon it when we come to analyze this particular code. And again, this is an example taken from the C++ Primer 5th edition, which you can buy on Amazon. It's a good book. In terms of, just as a side note, the books that I would recommend to learn C++, you have to read several books. And you have to read them in the correct order. And the books that I would recommend, and the order that I would recommend them in, is Michael Dawson's Beginning C++ Through Game Programming. It's not going to teach you graphical programming. It's text-based, but it's a good starter book. And then I would recommend C++ Primer 5th edition, and then I would recommend the C++ Programming Language by Jean Strojdrup that covers the entire language, and then you can move on to a whole series of different other different books. But those are the three books that you want to start off with. So as I say, this example is taken straight from the C++ Primer 5th edition. So let's proceed to, and I suppose I'll talk over this as I'm writing it. So we have the specification of a class called HasPtr with public access specification. We specify the constructor, which in this case will act as the default constructor. Okay, and we're just going to have to rip this out. So we have public access specification, and then we specify a constructor here which will act as the default constructor, and you will see why shortly. Okay, so I should be talking through this. The parameter is a constant reference to an object of type string found in the std namespace with a default argument of a default constructed string. And we are within the context of the constructor initializer list, and we want to initialize a representation. One of those data members is a data member called P, and we want to assign the return value of the new operator, which dynamically allocates an object of type string constructed with S. And then another data member is I, and we will discuss the role of I in this particular program. It's essentially useless, but it is meant as a dummy variable to help, well, within the context of the within the context of C++ primary 5th edition, it is meant as a dummy variable to uh, it's meant as a dummy variable to just demonstrate the different notions in terms of copying and so on. Okay, let's move on to our next constructor. We will discuss this at length shortly. We're specifying another constructor, and in the constructor initializer list, we're assigning it to the return of the new operator that dynamically allocates an object of type string, which is constructed from the S component of the object. Hold on, that's not correct. Okay, so we'll discuss what's going on here shortly. Oh, that's wrong. Pretend that's a comma. I is a dot I, and so on. So before we move, okay, we'll quickly, I'll talk over this as I'm writing it, but we'll discuss it at length shortly. So here we're specifying the prototype for the assignment operator. This is a specification of the destructor. And then we have private access specification with a pointer to a string and an int called I. And lastly, let's define the assignment operator. And we'll discuss this at length, as I say. And finally, we return the object upon which we call this particular member function, or this particular assignment operator. Okay, let's discuss this at length. So, as I stated previously, it would be helpful to have a background understanding in the basics of the C++ programming language, but I will do my best to explain most things in a way that is accessible to those who have not experienced it before. And so, what's going on here? The first thing is we're declaring a class, and we know that because we're using the class keyword here, we're using the following notation. And the class is HasPtr, and the class is C++'s main mechanism for expressing abstractions. And it is an abstract specification of how to create what we call objects or instances of that particular class that actually reside in memory. And the class is a relatively simple construct in the sense that it groups together two fundamental different pieces of information, data members and member functions. Now it's more complex than that because of course we have different access specifications, we have different interactions in terms of friend classes and so on, and a few other things. But the central notion of what a class is a relatively simple one. So what we're doing here is, as I say, we're declaring a class called HasPtr. Think of a class as a specification that groups together data members. What are data members? They're just objects of differing types. That can store different values. It should be intuitive to understand that, for instance, a data member could be an integer called x, and naturally that integer can, of course, store different integer values. Of course, it can't store anything beyond what it is permitted to, in the sense that in order to represent a value such as 10 billion, you would need more storage space, and so you can't do that. That's the general idea. So we're defining a class. Public access specification, which is here, that basically just states that general users of the abstraction can access the representation, or access the different components of the HasPtr class within that particular access level. Of course, if we were to write private here, then everything the access specification applies to everything that follows up until the point where another access specification is supplied, and the others are private and protected. We will not discuss those as of yet. I will get on to discussing what a constructor is, but to be succinct, a constructor is a mechanism for configuring the initial state of an object in order to give it some kind of semantic meaning. So this is the definition of a constructor, and the constructor has the same name as the class itself, as you can see. And the parameter is a constant reference to an object of type string called s, initialized with a default constructed string. We obtain a default constructed string with the following notation. We simply construct it by means of the function call notation. Really what's going on there, it's not actually calling a function, it is calling a function. It's calling the constructor, the default constructor, which means it will be the empty string, and then we are assigning that to a constant reference to an object of type string. If this was not a constant reference, we cannot do this because this is a temporary, and R values cannot be bound to L value references, so it has to be a constant reference to the object type in order to bind to an R value reference. This section here is what's called the constructor initializer list. It is basically a place whereby we can initialize different data members of the particular uh, initialize the representation of the class. And in this particular case, to be succinct, P is a pointer, as we can tell. It's part of the representation, and it is, where is it? It is a pointer to an object of type string. We assign it the return value of the new operator. What does the new operator do in this case? It allocates in dynamic memory, or on the free store, an object of type string, as we can see here, constructed from S. S, of course, is this parameter here, which is either going to be the empty string or some string specified by the user upon object class instantiation. Now, of course, you have to understand that the string implementation itself also handles memory management, and so consequently that will lead to further memory allocation, but we're not going to proceed or recurse down to those levels. Then what we do is we initialize I with a value of 0, and then we have no work to do within the body of the constructor. The copy constructor is also trivial, and we will discuss in detail. I have some notes prepared for this that we will review, and so consequently I will not go into it in too much depth at the moment. But this is a constructor, as we can tell by the fact that it has the same name as the class itself. And the parameter is a constant reference to a HasPtr object called A, which means that it will be invoked in context whereby we supply, in context of construction of objects of type HasPtr, if we supply an object of type HasPtr, it will invoke this particular implementation, and this particular implementation within the context of its initializer list will initialize the P component of the object we are constructing to the return value of the new operator, which in this case allocates an object of type string on the free store, initialized, which itself is constructed from the dereferencing of it is constructed from the value obtained by getting the P component of the A object and dereferencing it. What does that do? The P component of the A object is a pointer to a string, so consequently we obtain the pointer to the string, then we dereference it to obtain the string that it points to, and then we use that to construct the string that we're allocating in memory. And then of course we set I to A.I and so on and so forth. Now, one thing you have to understand is that with respect to all member functions of classes, there's what's called an implicit this parameter. And historically, the implicit this parameter was a pointer to the object upon which a particular function was invoked. But they've actually changed it, to my understanding, as I have learnt very recently by reading books. They have changed it such that it is now a reference. But the notation has not changed, in the sense that in order to obtain the object in order to obtain the instance upon which a particular member function was invoked, you have to ostensibly dereference the implicit this parameter in order to get that. And the reason for that is that there's so much code out there that's written using that notation that code would break if they were to change the notation. So consequently, they implemented a special case whereby the implicit this parameter is a reference but you can use the pointer notation in order to access it. So when we reference P here, because we're in the context of the constructor, it automatically knows that we're referring to the representation of the object we're constructing. Okay, that's fine. In terms of, this is a prototype for the assignment operator, the copy assignment operator, and this is the destructor. No, where's the destructor? There's the destructor. And the destructor in this case basically specifies if we allocate memory on the free store and we don't free that memory. So suppose we, for instance, have this specification for this class type, and we have block scope, and we create an object of type x called x. I'll leave it at that. In C++, whenever you local objects only live to the end of their scope. So consequently, when we get to this point here, this object will become out of scope. In its constructor, however, it allocated some memory. Now, the good thing is that, there's actually a technique there's actually a word associated with this technique. But suppose, for instance, that the destructor wasn't defined. In other words, it was automatically synthesized. In that particular circumstance, we wouldn't have freed the memory, and we would have lost reference to it unless we passed it out by some ingenious mechanism. But in general, we lose reference to it, and so consequently, we have a memory leak. Now, here's where destructors come in. The destructors are automatically invoked upon object obliteration, which will happen at the end of this block scope, and that will automate the process of cleaning up any allocated memory in order to prevent memory leaks. And here, the private access specification essentially means that this particular section does not give access to the general users of the class, but only the member functions, the friends of the class, etc. And we have one data member. We call this the representation, and we have two data members. One's a pointer to a string called p, and one's an int called I. Okay, let's move on to discuss the next one. So here we have the specification of the copy assignment operator for the HasPtr class, and it is in our case defined as a member function. Now, with respect to overloading operators, the way that it works in C++ is that you can overload the meaning of an operator when applied to particular objects of certain types, but there are certain things you can't change about operators. The most obvious one is the token utilized. That wouldn't even make any sense, because of course if that were the case, then really it would just be a matter of reconfiguring the whole setup. So disregard what I just said and listen to these following points. You cannot change the precedence levels and associativity. But what you can change and what you can invent is what particular operators mean when applied to objects of particular types. In this case, our particular copy assignment operator is a member function. Now, so in general, whenever we're defining an overloaded operator, for instance, an overloaded addition operator for the matrix class, then the operands of that operator correspond to the parameters of that particular function, and that's how it works in C++. Now, in this particular case, there is an implicit this parameter, and that implicit this parameter is a reference. I don't know if it's constant or not, but no, it's not constant. Of course, it's not constant. What am I saying? There is a reference to a HasPtr class, and that's the first parameter, but we can't see it. It's implicit. And then the right-hand parameter is a constant reference to a HasPtr called RHS. This particular copy assignment operator is invoked in contexts whereby the left-hand operand is an object of type HasPtr and the right-hand operand is an object of type HasPtr. And in this case, note that we specify const because we do not wish to modify the right-hand operand of the operator. So what's going on here in the implementation of this particular assignment operator? What logically... Again, keep in mind what we're trying to achieve here. We're trying to achieve value-like behavior, in other words, absolute independence. And so one could naively proceed to define the copy assignment operator as simply assigning uh, to the updating the representation of the target object with a representation of the source object, in the sense that the pointer in the source object is assigned to the pointer in the destination object, and thus we end up in a situation whereby both pointers point to the same location in memory. There are different problems with that, which we will get to discuss later on in the lesson. Uh, but remember what we're trying to do here. We're trying to provide the semantics of value-like behavior. And so what that means is that there has to be absolute independence. And so this notion that we can just assign the pointer, the data member that's a pointer in the source object, to the data member that's a pointer in the target object, you can't do that in order to provide value-like semantics. So what you have to do is as follows. Here's the algorithm that you apply. First, you call the new operator to allocate an object of type string initialized with a thing to which, let me say that again. I usually have a way of saying this. We use the new operator to allocate an object of type string, and that in and of itself is constructed from the thing that the p component of the RHS parameter, the thing that it refers to. In this case, it's a string. And the new operator returns a pointer, and we store that pointer in n. And consequently, auto will automatically reduce to a pointer type. Wait a minute, is that correct? Oh yes, I believe that's just for references. Okay. So here's what we do. We then delete p because we don't want any memory leaks. We set p to n. So what's going on here is, let's draw a little graph here. Suppose we have an object x, and this is the free store. We have an object y, and we want to set x equal to y. Then what we need to do, firstly you have to understand that this may already point into the free store. So that's the first point to consider. And this obviously points into the free store as well. We'll call this P, and we'll call that P. So what we want to do here in this particular implementation, this particular expression will invoke some unit of computation, and that unit of computation executes this particular statement here, which dynamically allocates a string and initializes it with the thing to which the P component of the RHS object refers to, and we return the pointer, the address returned is stored in n. We then delete P. So P points to this location here in the free store, and we release that memory to such that it's free for the system to use. Consequently, P points to invalid memory. We then set P equal to n, and P, let's suppose n was situated there. P now points to n. The values of the different strings, if we were to employ the equality comparison operator to the different strings stored at these different locations, it would yield true. Yet they are independent in all respects. In other words, not only do they point to different locations in the free store, but the strings in and of themselves are independent in the sense that a modification of one of them in one object does not affect the other. Now, we set the I component to RHS.I. Again, this is called member selection. It is the way of accessing a data member of a particular class type, or a class instance, and then we return this. And what this does, we return I always read it like this. We return the thing to which this refers. This is an implicit parameter that refers to the object upon which we initiated a function invocation, or initiated a function call. And this particular expression here conforms to the convention that we return the left-hand operand of the assignment operator, which is exactly what we do. So as you can see here, we get this value-like behavior given this particular arrangement. 1 second. Just looking over some things. Okay, so let's now discuss pointer-like behavior. And pointer-like behavior relates to uh, implementations that well, pointer-like behavior represent relates to objects pointing to sharing the same underlying resource. In other words, pointing to the same location in memory, for instance. Okay, let's start writing on some code here. Let me put on some music. I'll get copyright banned. So we have public access specification. Here's the specification of a constructor. That's wrong. I'll do that. So we're going to give it so this is the specification of a constructor that will act as a default constructor, and we, as a consequence of the fact, we're going to give it a default argument, which is the default constructed string. And in the member constructor initializer list, we will set p equal to the return value of the new operator constructed with s, I to 0, and something called use equal to the return value of the new operator, which allocates an object of type size underscore t initialized with 1. Okay, so here's the general idea before we continue. So here's the idea. We should probably discuss this before we continue on. The general idea is this. We want to provide pointer-like behavior in the sense that we want different instances to share the same underlying resources. And in this particular context, we would like the different instances of the class type to refer to the same location in memory, but there's potential trouble there. And that potential trouble lies in the very fact that we do not know when to delete, when to free a particular memory, when different objects go out of scope and so on, because it is possible to have nested scopes whereby in one of the outer scopes we declare an object of class type. Let's say for the sake of argument it is the class type we are defining, and in an inner scope we declare another object of the same class type, but we use the copy constructor to initialize it. To provide pointer-like behavior would mean that both instances would point to the same location in memory, Uh, but there's a potential problem in the sense that if the destructor were to just free the memory unambiguously, then the object in the outer scope would point to invalid memory such that any attempt to dereference its underlying representation would lead to a program crash. And so consequently, we need some kind of mechanism to keep track of how many different objects point to a particular uh, location in memory. And so the way that we do that is we make use of something called a reference count. And here's the general idea behind reference counting. The first thing we do is whenever we create an object of class type, we initialize a counter to a suitable value, namely 1, and that, in terms of its logical foundations, relates to the idea that one object of that particular class type refers to that particular uh, class object, refers to that particular string. Now here's the key point to understand. Uh, that the counter concerned cannot be stored in theory, we could actually make use of a static data member, but we're not going to do that. In this particular case, assume that we were working with local variables, then in that case, how could we suitably update the representations of different instances? Uh, well, whenever we copy, conduct multiple different copy operations. Uh, so the general problem is that we need some way of updating. We can't just store the reference count in each instance of the class because there's no way to update it in that circumstance. For instance, suppose we declared an object of type HasPtr called p1 and initialized it with the string hello, and then we created another HasPtr called p2 and initialize it with p1. In that particular case, p1 and p2 are going to point to the same string. And suppose that in that particular case we say, okay, logically speaking, what we can do is we can just peek into the representation of that particular the source object to get what is ostensibly the amount of objects that point to this location in memory, and just increment that and store update its representation, update my representation, and everything's good. But the problem is that doesn't go very far. It only works one second. So the general point is that in that particular case, it doesn't go far enough because uh, there is no way to suitably update the representations of the different objects that point to the same location in memory if we declare multiple different objects of type HasPtr that copy different instances of it. And so to be concrete, take an example straight from the book. Actually, no, we don't need to do that. Actually, no, we will do that. Suppose I declare, let me just, so suppose we declare an object of type HasPtr called p1, and we initialize it with string. We create another object that has HasPtr called p2, and initialize it with p1. In this particular case, we could theoretically peek into the representation of p2, increment it, update its representation, configure our representation, and move on. And then what we could do in the next statement is say HasPtr p3, p1, and so on. In this particular statement, p3, we peek into the representation of p3, there's all sorts of complexities here, as you can see, because of course, how do we define what the procedure should look like? Do we always look into peek into the representation of uh, the target object in order to come to a determination as to what the use count should be? In that case, it will never exceed the value 2. Uh, of course, whenever you're constructing the order in terms of the order that the different uh, objects are initialized, let's see. So, look, here's the general point. How do we suppose that the representation of P1 says that there's two objects? It peeks into P3's, it says that there's only one. In this case, it can't find out that information because of the way that the initializer list is structured. Uh, so let's say it peeks in, it may even find an undefined value. I mean, there could be a bug here. Uh, you know, actually, it depends. No, there can't be. There can't be because it hasn't been constructed yet. So here's the general idea. There is no way, in this particular case, assume that the P1 representation stores the value 2 and the P3 representation stores the value 0. And we have to, I'm just thinking we have to go back on our previous considerations. So here's a better way to structure because I made a mistake. Suppose that we peek into the representation of P1 instead, up here. We peek into the representation of P1, see how many objects point to the dynamically allocated string, and then increment it, update its representation, and suitably configure P2's representation. Then we go down to P3, where we declare an object of type HasPtr, and in this particular case we peek into the representation of P1, we see that its value is 2, we then suitably increment it, update its own representation, and then assign to the representation or configure the representation of P3 to store the value 3. The major problem is how do we update the representation of P2 in order to correlate precisely with with P3 in this particular case and P1? Well, the answer is that you cannot do it if you store an object, the counter, locally in the class instance itself. It has to be shared amongst the different instances. And so we achieve that by means of a data member called use, which points to dynamically allocated memory, in this case a dynamically allocated size t initialized to 1. It's initialized to 1 because of course we can only begin with one instance pointing to dynamic allocated memory. Okay, let's write out this code quickly. Actually, we'll discuss it as we go, just to make it easier. So this is the specification of a constructor which has a reference parameter to type string, and we set p equal to the return operator of new, which dynamically allocates an object of type string, constructs it from s, constructs I with 0, and then constructs use, which is in our case the data member, the actual pointer. What has to be understood here is that each instance has its own unique pointer, and pointers are objects in and of themselves, meaning that they have different addresses. What is invariant across all the different instances, so long as we adhere to certain constraints, is that the address stored in the pointer in terms of its value is equivalent. And what we mean by that is that we need a situation whereby the only mechanism for getting two different objects to point to the same location in memory is by means of copy assignment and copy construction. I just forget. I thought I was going to say something else. What? I just have to remember something. 1 second. Okay, I lost what I was thinking about. So, look, here's what's happening. As I said, we have this. Okay, so here's what's happening. It doesn't really matter what I was saying. Uh, we dynamically allocate a size t on the free sort, initialize it to 1, and initialize use with that. Oh, I remember what I was saying. So we have to ensure that the only way that a particular uh, object can point to the same location as another object is because it was copy constructed indirectly uh, or directly, or even copy assigned indirectly or directly. Because otherwise, if it was theoretically possible to manipulate pointers in such a manner so as to obtain a pointer to the dynamic memory and free it, for instance, then in that case, you would have a situation whereby the program would crash upon attempts to dereference the pointer in the different representations. But more interestingly, uh, if we stored that pointer in the representation of another object of class type that had a destructor that freed it, that could also cause some problems. Okay, so let's move on to discuss the next section. We have another constructor which has a constant HasPtr reference called A, and we will implement that as follows. In the constructor initialize list, we set p to a.p, I to a.I, and use to a.use. And here's what we do in the bodies. We actually have some work to do. We apply the postfix incrementation operator to the dereference of use. In other words, we dereference use and increment it. And that's all we have to do. And that, semantically means, logically speaking, we're doing that because uh, we have one more object pointing to the dynamic memory chunk. So once again, we will neglect to define the assignment operator, which is a member function in this case, within the context of the class itself. We have the destructor. We have private access specification. This is the representation, so we have a string, pointer to a string. We'll call it PS, an int called I, and a size t, which is an integral type, implementation defined, a pointer to it called use. Let me just do that again. Pointer use. So let us define the destructor. So this is the end of the class. So as I say, in terms of what's going here, let's just speed run through it. Specification of a class. Constructor configures the initial representation relatively simply. We have the copy constructor, which suitably increments the use, which is the thing to which use refers. Use refers to a dynamic. You have to understand is that within this context, we're dereferencing the use local to that particular to associate it with the implicit this parameter, and we can do that because we've already assigned to use within the copy initialization constructor initialization list the use component of the A object, which is the right-hand operand of the or which is the object, the source object that we're copying from. We have the assignment operator, which we haven't defined yet, and then we have the representation, different data members, pieces of information we associate with each particular instance of the class, and so on. Now let's define the destructor. And I haven't really discussed this because really, as I say, it's all about having a basic understanding of the C++ language. But the reason what we're doing, this is called the scope resolution operator. And the reason that we need it in this case is that we need to instruct the system that the function we are about to define, which is the destructor, which we can tell by this token, is within the context of the type HasPtr, the specification for the type HasPtr. And the destructor in this particular case does the following work. So first we have to check if the prefix decrementation of the dereference of use is equivalent to 0. And if that's the case, delete PS and delete use. So in other words, what's going on in this constructor? Well, suppose we create different, let's write it out here. Suppose, given our implementation that we've set forth, we create an object of type HasPtr called x, and it's just default constructed. And we create an object of type HasPtr called y, constructed from x. This particular declaration will cause there to be an allocation on the free store. And in particular, there will be a use data member that refers to a size t on the free store. Let's say it's situated there, just for the sake of argument. Of course, it's not to scale, it's not accurate, but it's just for the sake of argument, in terms of helpful diagrams and so on. Okay, what happens whenever we copy construct y with x? Well, in that particular case, y is such that it points to the same location on the free store, and we also increment that. Now suppose, for a moment, that we did that within another block scope, this particular statement here. Once we reach this point here, the y object ceases to exist, its destructor is run. And so consequently, we need some logic to determine whether or not we should free the memory associated with the y variable. And so to do that, we basically have to check the use count. In other words, what we do is we dereference use, which obtains the size t that it refers to, and we decrement it so as to obtain a value 1 less than its previous value, what is now its previous value, and we use the equality operator to compare it with 0. In other words, what we're saying is, if the thing to which use refers to decremented with postfix decrementation notation is equivalent to 0, logically speaking, that means that no objects point to this dynamic memory anymore, and so consequently we can free it by means of that statement. We can also free the use counter by means of that statement. Okay, we're ready to move on to some other examples. Okay. Okay, so the next thing I would like to discuss is something called swapping. So, classes that manage dynamic memory, that operate with memory at a low level, often define a function called swap. Uh, and the reason for that is that the swap function is utilized within the implementation of various different generic algorithms provided by the STL in order to provide the service of swapping two objects. Now, in terms of our implementation, how could we potentially swap two objects? Suppose we have an object of type HasPtr called x, and we have an object of type HasPtr y. We just say they're default constructor for the sake of argument. And we want to swap the values of x and y. How do we do that? Well, logically speaking, we very simply create a temporary. So we say HasPtr temp is equal to x. X is equal to y, y is equal to temp. So that's the way we can swap values. And the reason, as I say, for defining a custom, here's the general idea, and we're going to discuss this very shortly. Okay, let's actually discuss this first. Here's the problem. We can observe or consider the inefficiency with respect to memory allocation, taking into consideration our implementation of this particular class. In other words, we have to allocate memory in order to create this temporary here, and then we have to call the copy assignment operator in both these cases here. But there is an inefficiency here with respect to memory allocation that is unnecessary. One second. So I think I've already said this before. The reason that you would want to look, here's the general idea. Different algorithms in the standard library are implemented in terms of a call to the swap function, and there is a standard swap function. You can access it by means of the following notation: std : swap. This particular function is implemented in terms of the same logic employed here. And here's the problem. If you're dealing with classes that handle dynamic memory, then the problem is that this can be a relatively expensive procedure to execute, and so consequently, it becomes reasonable to consider the implementation of a custom swap operation that optimizes this fundamental operation such that the algorithms can operate faster. The reason why those algorithms swap, maybe they're sorting a sequence of elements and so on. And so, because of the inefficiencies associated with our implementation of the HasPtr, this particular conventional swapping procedure, what we would like, when we think about it, swapping two values doesn't have to entail the creation of the temporary, because realistically speaking, the only thing that's going to change, I mean, you think through it logically, the only thing, the objective you're trying to achieve is that the strings point to memory, dynamically allocated memory on the free store that stores a string represented by the corresponding or the opposing object. Let me rephrase that. Logically speaking, whenever we for instance, in our example, whenever we want to swap two values, there's no need for the extra memory allocation, because logically speaking, the only thing we're trying to change is the strings to which they refer. And so consequently, it's much more efficient to just swap the pointers. And so consequently, it would be ideal if our implementation of the swap operation could be implemented as follows. We create a temporary string pointer called t and initialize it with v1.p. we say v1.p is equal to v2.p, and v2.p is equal to is equal to t. Now, as you can see here, no expensive memory allocation, still the construction of a temporary, but that's necessary logically speaking. At least we think it is, okay? So anyways, that's what we would like our implementation. In other words, here's the general motivation for this. We want to implement, because of the employment of the swap algorithm in many different algorithms, we want to implement a swap operation that is optimized so as to speed up the execution time or computation time of our algorithms. And so consequently, what we can do is suppose that, here's what we're going to do. We're going to define our own custom swap function. And to do that, what we do is we go to the specification or declaration and definition of the HasPtr class. And the first thing that we do is that we declare that this custom swap function is a friend of HasPtr. And the reason we do that is because this particular swap function needs access to the implementation of the HasPtr class. And then we have the other implementation details as before, indicated by these dots here. Inline specifies to the compiler, and again, inline is an optimization technique that can be employed with relatively small functions to basically take the implementation of the function and just expand it wherever we invoke that function, such that it's almost as though we just wrote the instructions at the point of expansion. But in terms of how we would actually implement this particular efficient swap operation, we can implement it as follows. Specify that it's inline once again, returning no value as indicated by the keyword void. It's a function called swap, and we have a reference to a HasPtr called LHS, a reference to a HasPtr called RHS, and what we say is as follows. We want to swap LHS with .p with RHS.p, and we want to swap LHS.I with RHS.I. Now, in this particular case, we need to instruct the system to make visible the standard swap function, and we do that with this using declaration here. And in terms of what's invoked in these particular function invocations, it is the standard swap function, and that is implemented in terms of the logic we considered previously. So in other words, we have considered a more efficient way to swap the values of two objects by manipulation of the representations in a suitable manner, and that's fine. Now here's the important point to note. Whenever you have, as in our case, the HasPtr class, a class with various different data members, you have to understand that some of those data members don't have custom defined swap operations for them, and so consequently, in order to swap them, you have to use the generic version. But other data members may have actually been optimized with a specialized swap function, and so consequently, we would like to use that swap function within the context of the implementation of the swap algorithm for that particular class type, in this case the HasPtr, and that really relates to the one here with this particular signature interface. Now, in order to, if we said std colon colon swap, if we use the notation std scope resolution operator swap before each function invocation, then it would uniformly and unambiguously uh, use the standard version of it and not the specialized version, which would mean that it would be potentially less efficient and thus lead to slower computation time. Which is not what we want. So here's what I would like you to observe. Observe the implementation of our custom swap and consider a case where a data member was of a type that optimized this operation by defining a custom swap. So just consider that statement, that proposition. So the next thing I would like to discuss is using swap and assignment operators. So here's how we could potentially define an assignment operator. We could actually define it in terms of swap. I'll write that again because it's not very neat. Okay, let's just go down a little bit. So we want to define this operation in terms of swap function. And in this particular implementation, again, I haven't given much consideration to it. I probably should have in preparation for this. I have for other things, by the way, but in this particular case, I haven't. There could be inefficiencies in here. If we isolate purely the specification of the arguments there is, because we're copying by value here, which will invoke a copy constructor. We're not using a reference, and so consequently some memory allocation may occur. But the reason that we have to copy by value is because we're implementing the assignment operator in terms of the swap function. And in an assignment operator, semantically speaking, you want the source and the destination objects to essentially represent the same value, and so consequently it wouldn't make sense to define the parameter as a reference. So that's why it, logically speaking, needs to be copied by value as opposed to reference. Now, the next thing I want to talk about is and I'm going to discuss what I prepared some notes of maybe a few days ago in preparation for this lesson. And by the way, if you think I'm not being thorough enough, or you think I'm being too verbose, or you think I would like to improve, you think I should improve on certain things, do comment below. If anybody ever watches this, which will never be the case, I hope. I hope. What am I saying? I I hope people watch it. Anyways, the next thing I would like to discuss is implementing a move constructor and so forth. And I have some notes in preparation for this, and I will proceed to read them. So, let us discuss what a move constructor represents. First, let us discuss fundamental concepts of concern related to this matter. What is a class? The class is C++'s main mechanism for creating what are called abstractions. They are fundamentally very simple. They represent a mechanism for grouping together the two kinds of entities, data members and member functions. We refer to the totality of the data members of a class as its representation. Data members are essentially values of specified type that can of course store a value in memory. The type dictates two primary things: the amount of storage to allocate per instance, the way to interpret the bit pattern stored in this storage. Member functions, on the other hand, represent units of computation which are crafted from ordinary C++ code and thus can do anything allowed within the context of the language that are in order to be invoked. must be that in order to be invoked must be uh, must be called on behalf of a particular instance of a class, a topic we will discuss shortly. This is a this is a greatly simplified overview of what a class is, but it is the fundamental nature of the construct. Also note we are in particular simplifying member functions. Now, the class definition is an abstract specification for which we need to the class definition is an abstract specification for which we need not allocate any storage. We can create particular instances of the class or instantiations by declaring a variable of a class type which are conventionally semantically independent. So, these devices simply adhere to a set of rules specified by the C++ standard. Thus, they have no associated semantics and can, consequently, in theory, be used in any way the language allows. However, typically we will use techniques to enforce some logical objective. Typically, the representation is inaccessible to general users of the class by means of private access specification. Then, the member functions provide the mechanism for manipulating the underlying representation in a way that is reasonable, efficient, and maintains class invariance. An interesting question arises from the preceding discussion. How do we provide an initial state for an object of class type? That is where constructors enter our story. Constructors. What are constructors? Well, in terms of their technical content, they are specialized units of computation automatically invoked upon class type instantiation on behalf of that instance. What must be understood is that the implementation of the constructor need not be reasonable or semantically sound. It can do anything, whether it be printing a value to the screen or computing the result of some arbitrarily complicated expression, the result of which need not be used in any meaningful way. However, the key is in the name, constructors. As the name implies, the goal of the constructor is to construct or configure the initial state of the object, which may provide initial values to some data members and allocate some memory. One second. Anyways, let us move on to discuss. So, now, we can specify that the constructor have parameters. We refer to this as its interface, as this represents the means of interacting with the function's implementation. Thus, we can specify that a constructor has an integer parameter, meaning that provided suitable notation, it will be invoked when we provide an integer. Thus, we can define any parameter set and have that constructor invoked given the supply of suitable arguments. Now, there is an interesting consequence of this. We can, in theory, specify a single parameter. So here's what we were discussing. We're discussing the fact that the constructors can have different parameters, and there's an interesting consequence to that, and it is as follows. We can, in theory, specify a single parameter of the class type itself. This has conventional semantic meaning, and we refer to it as the copy constructor. The key observation is that this special constructor, which we call the copy constructor, is just a regular constructor that is automatically invoked in context where we supply an object of the class type to which we can associate semantics and thus a name, the copy constructor. Again, observe that the implementation of this unit of computation does not necessarily have to provide the function of copying the value, but it conventionally does. Let us justify the following section by an example. Suppose we have the following code fragment. One second, I just have to get tea because I'm very thirsty. Okay, one second, I just have to sit down. So anyways, let's consider the following code fragment. Let us hypothesize about certain things. Suppose we have the following class definition. We have a class called X with public access specification, with a constructor with an integer parameter, the implementation of which sets one of the data members, which is a pointer to an int, to point to a dynamically allocated array of size s, so what's going on here in this particular statement is we'll just go down to the bottom here. Actually, I don't know how much room we'll have. In this particular statement here, p is a pointer. It's part of the representation of the x class. We dynamically allocate an array with the following notation on the free store. And so consequently, the amount of memory allocated will be the size of int, in this case, multiplied by the integer s. So if we specify 10, it will be 10 multiplied by the size of int, and so consequently there will be 10 ints in that allocated memory. It's an array. We can index it. Of course, array arithmetic is implemented in terms of pointer arithmetic. I can't remember the precise details, but I'll go over that at some point. So we dynamically allocate that array, return an address to it, and store in P. And the next thing we want to do is we want to, just for the sake of argument, give initial values to each element within the array that we just allocated. And we can do that as follows. We can use a for loop. Let me be very clear about this because I'm writing it. So we use the auto type specifier to declare a variable of type x, initialize it to 0. Check that x is not equal to s as our condition, so as to ensure we don't try to write beyond the confines of the memory allocated. If we increment x, and then within the implementation, we ask if x p indexed at position x is equal to p indexed at position x negative 1 multiplied by 3. Else p indexed at position x is equal to s. So what we're doing here is we check that we have the initialization portion, we have the the expression portion. We, we, we may refer to it as that. And what we do is we check, uh, we have to check, we want to use the values previously stored in the array in order to define what the element value should be for a particular location in the array. And so consequently, we have to implement logic that ensures that we're never looking uh, outside the confinements of the memory allocated. And so consequently, if we just had a statement that said that just assigned to indexing the array P at position X the result of this expression, then we would be attempting to access a memory location outside the confinements of the allocated memory and multiply it by 3, and that will cause undefined behavior, which is not something we want. And so consequently, we need to implement some logic to ensure that doesn't happen. And we do that by checking that if x is the target of the if statement, it is implicitly convertible to bool. In that case, the conversion operator will essentially check if it's non-zero. If it is, it will return true, otherwise it will return false. And so consequently, if it is true, that means that x is more than 0, meaning that we have populated it with at least one value, and so consequently we can say we index the array P at position X by means of this notation, which is a dynamic array we've allocated up here, and we assign it the value stored in the previous location multiplied by 3, otherwise we assign it that. Okay. Okay, so let us also define the destructor in order to prevent memory leaks. And then we have our private access specification. With two different data members, a pointer to an int called P and an integer called size initialized with a value of S. That's not right. Okay. So, take into consideration the previous code fragment we just wrote out. Suppose we would like to implement a copy constructor which is to provide the service of copying the value from the source to the destination. How do we implement this appropriately? Well, if we wish the destination to be independent, yet disregarding addresses equivalent in state to the source, we must conduct the following procedure. Step number 1. Dynamically allocate a fixed size array on the free store equal in size to the one allocated for the source, a number obtained from the size data member. We then employ a for loop to copy the elements of the source array to the destination and update the representation appropriately. Thus, we can implement the copy constructor as follows. Note, we use reference parameters for efficiency, const in particular because we do not wish to modify the source, a topic we will return to later. So in other words, here's how we could implement the copy constructor. We'll just write it out abstractly. So the copy constructor, of course, is going to be a constant reference to an object of class type. In this instance, we give it the parameter a name. And what we do is we set P equal that's wrong. Okay, we delete P. We then set P equal to a dynamically allocated array events of size of the S component of the A parameter, and then the for loop will populate it with values. And fairly simply, we say that P x equal to A dot P x. Perhaps that's not very helpful, me talking like that's just the way I talk through code, but we're indexing the array P at position x. It's defined in terms of pointer arithmetic. We're assigning to that position the result of indexing the array that the handle A. A is essentially a handle to a dynamic array on the free store. It's not a dynamic array in the sense that it can be resized in and of itself. You can of course have a vector implementation implemented such that it is in and of itself dynamic, but in order to achieve that, it has to free up memory and reallocate larger arrays and so on. But here's what's going on. We want to access the array within the context of the A parameter, which is the source object, and so consequently we use member selection to obtain the P array, and we index it at position x, assign that to the appropriate location in the target array, and so on. And then of course we have to update suitably the S component. Now, observe the following. I should perhaps go down. Now, observe the following. In theory, we can implement this operation much more efficiently. What we could do instead is simply assign the source pointer to the destination and update the S component appropriately. However, there is a problem, as illustrated by the following code fragment and diagram. So suppose, for instance, we create an object of type x, which we just specified, like so, and then we have another block scope, within the confines of which we create another object of type x, but this time we use the copy constructor, and this is point y. Now here's what you have to understand about this, and I'll draw a complementary diagram. So here's what we have to understand about this. The first point is that whenever an object, the lifetime of a local object is dictated by the length, the amount of time, the length, or it is determined by the time, because of course whenever we exit block scope, it depends on how fast the instructions have been executed. But block scope essentially dictates the lifetime of local objects, and so consequently in this case, this particular instance here will go out of scope at point y, and so consequently we will free up the memory associated with it because we've already specified the destructor down here. Again, we're hypothesizing that this copy constructor just copies the pointer and updates the S component suitably, and observing what could happen when this particular instance goes out of scope. So, as indicated by the diagram, the operation reserves the operation results in two independent objects pointing to the same location in dynamic memory. That seems to work fine. However, it does not. Correctly, we note that the destructor frees the allocated memory, and it will be invoked on behalf of the x2 object instance at point y. Thus, the object goes out of scope and ceases to exist, and appropriately frees the memory. However, observe that we have a problem. We now have an object pointing to an invalid location in memory. Our particular implementation has two major problems. Any attempt to dereference the representation will cause undefined behavior, leading the program to crash. The second problem, we call the delete operator twice in succession, potentially, on the same location in memory, which will lead to a program crash. We could attempt to rectify the situation, but we will not. The point of the previous remarks was to justify the development of what we call the move constructor, which conventionally semantically implements these kinds of efficient copy operations. Move constructors. First, we remind ourselves of an observation made in previous remarks. A move constructor is just a regular constructor with a specialized interface. However, it does not make sense to say that its implementation can be arbitrarily. Let me repeat that. However, it does not make sense to say that its implementation can be arbitrary, as the term has semantic meaning attached to it. Now, in theory, move constructors have always been possible in C++. However, they are most effective in contexts where the argument specified to its interface is about to expire, which entails which enables us to steal its value. Thus, they came to prominence in C++11 with the introduction of the R-value reference, which combined to a temporary. Thus, we can specify the interface of a move constructor in terms of an R-value reference to the class type of the following form. So here's how you would specify the move constructor. And again, it's an R-value reference, as we have just previously documented. Now, the job of the move constructor is to efficiently copy the value of another object, the source, into the destination. Note that this value need not be storage directly controlled by the class instance. The conceptual value also includes the dynamic array that the representation refers to. Now, taking into consideration that we have already documented the most efficient solution, which is significantly computationally expensive. Now, taking into consideration that we have already documented the most efficient solution, which is significantly less computationally expensive than allocating memory and invoking constructors, and constructors, for instance, which could in theory allocate more memory, and so on. Note that the move constructors must also achieve two additional things. Number one, it must be logical. In other words, especially considering the ephemeral nature of the source, it would not make sense to not update the representation of the source when the destructor is about to be run. Number two, it must leave it in a destructible state, the source. Let us proceed to implement the move constructor for our example class. Here's how we could implement the move constructor for our particular example class. So as you can see here, the constructor initializes list simply assigns to the p pointer, the p data member, the value of the p data member of the A object, to the s data member, the value of the s data member of the A object, and then it assigns to the p data member of the A object the value of 0. Now what's going on here is that we're effectively stealing the handle to the dynamic array uh, from the ownership of the A instance. That's precisely what's going on here, and that's a much more efficient operation, and especially in particular contexts. Here's something I would like to note. Note the efficiency techniques. Note the efficiency techniques here. Okay, so note the efficiency techniques here. We construct the object in the initializer list in order to avoid the cost of default construction and subsequent copy assignment. If this was computationally expensive, we would obviously have a significantly less efficient program. So, as you can observe, the implementation is trivial. This is characteristic of move constructors, as they in essence involve a minimal amount of work. For instance, copy a pointer, which is a relatively very efficient operation, although in terms of reasoning about it in isolation, may in theory not be as efficient as possible. Now, we have implemented a move constructor which efficiently exchanges the values, the destination, with the source. One final note. It is often stated throughout the standard that the value of a move from object is no longer defined and thus that object should not be used again. However, this is not an implicit limitation. It is perfectly possible to continue to use an object that acted as a source for a move operation, provided that the implementation of the move constructor leaves it in a reasonable state. Note, this is especially applicable to objects that do not expire soon after the operation. Note, this is especially applicable to objects that do not expire soon after the operation, as they were converted to an R-value reference by means of the standard std: move function. In other words, the standard move function returns an R-value reference to an L-value, for instance. Note, this is not particularly important for temporaries. So note that this is not particularly important for temporaries. Okay, one final point. In theory, the previous remarks don't quite make sense from an efficiency standpoint. The point is that if a true temporary were ever to be created, why not just configure the representation of the destination object directly? In principle, doing otherwise is actually less efficient, as we call a constructor, allocate some memory, and then do one extra unnecessary operation by copying a pointer. The reason is typically that it is a logical problem imposed by the very structure of the program, and thus remains impractical to do otherwise. So that is the end of my remarks with respect to move constructors, and so consequently I would like to proceed to implement a move constructor for our particular implementation. Let's go up to the top here. So this is the move constructor for our HasPtr class. So here's how we could implement it. Okay, so as we can see here, we have as I was discussing, this is a constructor, and we know that because it has the same name as the class itself. The interface is an R-value reference to the class type. We specify to the compiler that it's no except, meaning that it's not going to throw an exception. And in the constructor initializer list, we set p to x dot p, I to I dot p, and then set the p component of the x object to 0. Of course, that's an R-value reference, meaning that it's going to affect the original copy. And it's as simple as that. We now have a very efficient operation. Now, there's one last thing to note about all of this, and that is that is how to define the assignment, the copy assignment operator, and we will discuss that now. So let us define the assignment operator. Note, this is by value, and the reason that is the case will be explained shortly. So what we can do is we can implement the assignment operator, copy assignment operator, in terms of the swap operation we specified earlier on. And of course, the assignment operator typically returns a reference to its left-hand operand, and that's exactly what we do here. So, in terms of what's going on here, you have to understand. One second. So here's the point. Because we know what's going on here, we've discussed it at length previously, but because we've defined this as a non-reference parameter, it means that as a consequence of the introduction of the move constructor, that particular class, in this instance HasPtr, effectively gets a move assignment operator. And the reason for that is as follows. Whenever we pass an R value as the right-hand operand to an assignment operation, the target of which is an object of type HasPtr, then in that instance the move constructor will be invoked to move construct the parameter. In this case, it is a non-reference parameter, so it will invoke the move constructor, and so consequently, we will steal that value. And once we're in the context of this, we don't even need we don't need it in either case, but specifically in this case, we don't need the value of RHS at all because we're copying it by value. So consequently, we can just swap the thing to which this refers with RHS and discard RHS. This also works for the case where we copy by value. In preparation for these tutorials, I was going to go over and sort of consider the inefficiencies relating to this particular operation. One second, let's do that very quickly. Okay, so in terms of what's logically going on here, which must be understood is that because we're swapping the representations, we've defined a custom swap operation for HasPtr, and so consequently, the pointer stored in the object to which the implicit this parameter refers will essentially end up being stored in RHS, and the RHS destructor, the destructor for RHS will be executed at some point, which will appropriately free the memory that used to be associated with the left-hand operand of the assignment operator, and so on. And so that's the first point to note. Anyways, I didn't really have much time to sort of sit down and consider this particular code fragment in great detail in terms of actually trying to understand if it's efficient or not. It certainly doesn't seem to be very efficient on the face of it, because of course we're copying by value and so on. And swap is implemented as such an efficient operation such that we need not consider it, and so consequently we only need to consider the way the parameters declare and so on. But that'll be for another day. I'll perhaps talk about that in the next lesson. So this was a long lesson today. I hope you enjoyed. I hope you learned some things. It was a very simple example to get things started. But don't worry, we're gonna uh, take things up to the next level as we progress throughout the weeks and move on to progressively more complicated examples. So with that, I hope you enjoyed the tutorial and see you next time.